Okay, covalent compounds. All right, so here's the situation. You already watched the video on ionic compounds. Now I'm going to go through covalent compounds. So we're going to do some of the properties here, and then there's another video already on demand that compares the both. And once you watch all this, we do a virtual help desk, you guys should be good to go. And I'm also going to, you'll see a FET that I'm doing on the on-demand video. I'm also going to do another video with the FET through Zoom that'll really make sense. So I feel pretty good about where we're going with this, so you better pay attention. And if you watch the reflection video, you know this stuff's going to be really important. Okay, so yesterday we talked about sodium and chlorine atoms, crazy, transfer valence electrons because they need a full outer shell. They bond like this, hold on, like they pound fists because they're cool, they're happy, right? But they can, once they're ions, they can get pulled apart and dissolve. But now we're talking about not a, here you go, take it, boom, we're cool. Now we're talking about this, a share. So I want you to watch this video carefully. Okay. So now we're going to take, I'm going to do a simple, what I'm going to do, diatomic hydrogen. Okay? It's right there, I got H2. So we know it's non-metal, non-metal. Okay? So now hydrogen has one valence electron. I'm going to draw the other hydrogen over here. I'm going to give it an X for a valence electron, just like that. I'm just going to put it right there for ease. So this hydrogen says, this hydrogen, give me your valence electron now. This hydrogen says, back off, give me yours right now. So therefore they, it's not like, here, take it, you can have it. No, they are going to fight. So what happens when you fight? Eventually you're going to have to share and cooperate. So right here, this hydrogen has one of its own access to another. This one has a full outer shell. This hydrogen here has one of its own access to another. This one's happy. This one has a full outer shell. So when we draw this, we don't draw it with a circle and dots and things like that. We draw it like this. Because in hydrogen's case, a full outer shell is two valence electrons. So do you really think that this is going to want to, as we call it, dissociate in water and split apart? What would happen if it did? It wouldn't have a full outer shell because it's holding on for dear life. They're holding those valence, they're tight. Holding those valence electrons, they're not going to let go until you add enough energy for chemical reaction. That's the next chapter. So again, whereas before it was here you go, take it, okay, we're cool, pound fists, we can dissolve and dissociate. These guys ain't going to want to dissociate, okay? So here's another example. Let's do hydrofluoric acid. And you'll learn how to name all those soon. HF. So here's hydrogen. Here's fluorine, halogen. 1, 2, 3, 4, 5, 6, 7. And again, why am I doing it a little different? I want to leave this empty here. Okay. So hydrogen says, give me a valence electron now. Fluorine's like, no, I need to gain one. So all of a sudden they decide to share. Okay. So right here you're going to notice that these guys share. And do you think hydrogen is going to want to dissociate and let go? No, because what would happen? It would lose access to this valence electron. It wouldn't have a full outer shell. So hydrogen has its own access to this one. It has two. This one's happy. That's the check mark. Here, 2, 4, 6, 7. Access to one more, 8. This one's happy. Again, if this dissociates, it's not going to be happy. So we call this hydrofluoric acid. But if you notice, there's not many electrons over here, and there's a lot over here. This is something that's called polar. Okay. So, you see the difference. They're not going to want to break apart, so it's a stronger bond than ionic. Okay, polar versus nonpolar. So a polar compound would look like this. We'll go, let's do H2O. That's easy. And we'll get more into electronegativity difference. We'll get into polarity a little bit more in depth, but for now this will do. So right now the oxygen is up here, and I'm just going to draw it just like this. Just like that. I'm not going to get into that. You can do that next 2 levels from now. So hydrogen right here. Oxygen has 2, 4. This is a shared pair 6. This is a shared pair 8. Hydrogen now has 2. Hydrogen now has 2. How did I get that? Don't worry about that. All I want you to look at is this. This is positive, positive. This is negative. Why? There's more excess valence on this side of the molecule. This is something that's called polar. So this is the negative side, this is the positive side. Nonpolar, on the other hand, take a look at diatomic fluorine, F2. I think you can still see that. So let's bring in an F right here. Right? So there's 7 valence electrons. Here's another fluorine. I'll draw them as X's. Here we go, right here. Shared pair right here. This wants to gain 1. Well, this one has access to this one. Now this one has 8. So it has 2, 4, 6, 7 of its own. Access to that one, 8. Here, 2, 4, 6, 7 of its own. Access to one more, 8. This is a shared pair. So if you notice now, we draw it like this. This becomes this. So let me color code it. So this little mess right here, where they share, and we'll learn more of this later in the week. This is this. What about this over here? You got to draw them. So this fluorine has 2, 4, 6, 7, 8. This fluorine 2, 4, 6, 7, 8. Now, this has 6 excess valence on this side. This has 6 excess valence on that side. So the number of negative valence electrons, 6 valence over here, 6 valence over here, they cancel out. This is nonpolar because these 2 negative ends cancel out. So this is nonpolar. So what you're going to learn here is with covalent compounds, polar substances, right? Polar things. Why can polar dissolve in other polar things? Well, charged particles can dissolve in other charged substances, and we're going to learn about that. Water can dissolve many things, okay? Nonpolar can only dissolve in nonpolar things. Again, you'll have more of an appreciation for that later. What you'll see on the FET in about a day or so, we're going to have water on the FET, and we're going to drop a polar molecule in there, and it'll dissolve, but it won't break. Then I'm going to drop something that's ionic, and it will break. But we're going to wait on that a minute. You're not ready for that yet. You'll get ready for that soon. Okay. So again, all you need to know is non-metal, non-metal share. Stronger bond than ionic. There's 2 types, polar and non-polar. Polar can dissolve in polar, non-polar dissolve in non-polar. You'll see more of that soon. If you're a little bit fuzzy with that, don't worry about that yet. Okay, so then, they do not conduct electricity. Because why? You need free flowing, dissociated ions to have that happen in solution. So somebody asked a question today, something to the effect of, can an ionic compound dissolve when it's in its liquid form? And the answer would be no, it has to be dissolved and has to be dissociated. The compound has to dissociate in its free ions to conduct electricity. Now, covalent compounds do not conduct except one type that can dissociate, and they are acids. So acids are the exception for the most part. Strong acids dissociate quickly and have a lower pH. Strong bases also dissociate quickly and have a pH, but don't worry about that strong acid-base thing. Just know acids are the exception. So they do not conduct, except acids can, okay? Because they don't dissociate to free ions. Acids can dissociate, but don't worry about that yet. That's going to be next month. The next thing I want to tell you about is with covalent compounds. Is when I'm looking at my script, I got to remember all the solubility. Okay, we talked about that. Polar, non-polar goes with polar, non-polar goes with non-polar. Okay, melting point. So yesterday I showed you the brick of NaCl. This is big. Watch this. Remember how NaCl, they can dissociate, but now remember how we said one NaCl gets attracted to another one because they're stupidly negative and stupidly positive? Like that. And we had these electrostatic attractions in between them. And I'll draw one more. And the analogy, I'll tell you, when we have lots of ionic compound, when you have an ionic compound, these electrostatic attractions are almost like Legos. You ever take 2 Legos and try to pull them apart? That's analogous to an ionic compound. A covalent compound is like jumping into a ball pit. Like they're attracted to each other, but they can easily move away from each other because these forces of attraction aren't as strong. And the most common one that we see is water. And I'll show you once again. Water, if you have H2O, Yeah, this is a positive end, and this is negative, and this is positive. Not as positive as that. Not as negative as that. But it's still positive. And now, here, I'll even exaggerate the positivity here. I mean, that is ridiculously, stupidly positive and negative. Right? Here it's positive and negative, but it ain't as strong. So therefore, how would you, so are the forces of attraction between each molecule going to be strong? Not really. We call this the intermolecular force, the hydrogen bond. Let me move that from that glare. So right here, there is a force of attraction, but it's not as pronounced. Therefore, we have the other H2O right here. Again, there's positive and negative ends. It's polar. And they're attracted to each other, but not as strongly. So therefore, does not take as much heat. Can easily cause that to melt and boil. So covalent compounds have a lower melting point and boiling point. Ionic compounds have a higher melting point because you need a lot of energy to impact, to reduce these forces. Do you understand what I'm saying? Here, you don't need as much heat to reduce those forces. So the thing you need to understand is covalent compounds have a stronger chemical bond because they're held tight together because they don't want to break apart because they will lose their full outer shell. Ionic compounds, on the other hand, have their full outer shell. Their bond isn't that strong, but the force of attraction is really strong. That's the difference right there. Okay, so those are the main key points. And then you're going to watch this, and then you're going to watch another video from last year on demand. All right, keep coming up with questions on the Padlet. This is really important.